Right, folks, so we need to move on to new topic, okay, which means we have finished all of our AS topics. We are now moving on to the A2 content. And answer your questions, I don't actually have any Chemistry 2 books to give you at the moment, okay, but we will make do without the book for a little while, okay, probably until the end of June, yeah? A new green book. I have a couple of new green books for you, if you wish. Who is oh, you're all desperate for a new green book. Oh goodness me! But you all what? You're going to do the A2 in a new book? Okay. Who wants to go down and get me like 6 or 7 books? Ahmed, you're nearest to the door. It means you have to put your bag down as well, which is always a good plan. Okay. So you want one. You want one. Go, go, go. About 7. Sorry, they all go to this table here because they're right in front of me. Okay, so the first topic that we look at together, I believe topic 11 and 12 you will do with Mr. Collins. I think he may have started equilibrium already with you, yeah? So the first one you do with me is further energetics. Okay, so energetics meaning what exactly? Tell me. Enthalpy changes, exactly. Okay, so I thought a nice place to start for today. We're going to take it nice and easy. We're also going to split our time a little bit over the next couple of weeks between doing some revision and doing some new stuff. Okay, definitely Thursdays are going to be a self-study kind of lesson. Okay, for 45 minutes, and then possibly another one where I'll do some revision with you as well. Okay, so we'll sort of split our time in half. But like I say today, further energetics, what you must be able to understand before we even go on to learn anything new, everyone must be able to work with and draw and understand Hess's law and Hess cycles. Okay? Hopefully you will understand this by now and you feel very confident with it. Yes? No? Yes. Kind of. There's some fairly sheepish looking faces there that say, I'm not totally convinced about this. Okay? Which is fine, it's okay. It's also good revision for our AS topic of energetics, okay? Which is probably mostly what we're going to do today is a little bit of revision to make sure you know what on earth is going on. So who can tell me, what is the actual principle that underpins Hess's law? It's like a overarching scientific principle. James?
So Hess's law is no matter what path you take, if you go from A to B, no matter what path you take, the enthalpy change will always be the same.
Exactly. So no matter what path you take for a reaction, the enthalpy change will always be the same. It's really just an extension of conservation of energy. Yeah? You know that energy is neither created nor destroyed. That's kind of a massive principle in physics and chemistry and science, even in biology. Okay? Energy cannot be created or destroyed. So, in general, it says that if I take A plus B and I make C plus D, there's an enthalpy change of that reaction, yeah? But I can take alternative pathways. So I could to make C and D, I could go around this way and make, on the way, E and F, but then take E and F to make C and D. Yeah? And that would be, I call that delta H1, and that one delta H2. Okay? And if I take the principle of the conservation of energy, then the enthalpy change from here to here is exactly the same as going from here to here and then up to here. So the delta H of reaction that we're looking at in this case is equal to the enthalpy change number 1 plus enthalpy change number 2. Okay? So that's like a kind of general Hess cycle. Okay? But I think, and I was chatting to someone yesterday about this, okay, I think actually everyone understands what they should do, but then they look at a question and the question throws them off completely in terms of the way it's worded and what you have to do. Okay, because I bet if I ask you right now, right, there's generally two different ways we do Hess cycles. What different enthalpy changes do we use in our Hess cycles?
Usually combustion and formation.
Yeah, so they're enthalpy changes of combustion or enthalpy changes of formation. And again, I guarantee if I ask you, if I'm using enthalpy changes of combustion, what direction do these two arrows go in? Downwards. There you go. Okay? And if I use enthalpy change of formation, what direction do these two arrows go in? Up. Yeah? So where does the confusion lie? That's the question. Okay? How does it suddenly become really difficult when you see a question? Okay? The answer to me is that it shouldn't seem that difficult at all. Okay? But you've got to look at what the data is that you're given. Okay? Quite often in an exam question, thank you Ahmed for going down and getting those, that's awesome. Go on, give them out. Thank you. I'll let you do that for a sec before I carry on talking. Anyone else need a book? Nope. Excellent. So, when you use if we use enthalpies of combustion, delta H C, hopefully that's the way that Mr. Collins writes it as well, yeah? Okay, there are different combinations of where you put the letters and stuff, but that's the way I always write it. So when you use enthalpies of combustion, I'll just write a general one. Then the arrows go down. Essentially you're saying whatever this is reacts with oxygen. So it could be AO plus BO. Interesting way to put it. Because it's reacted completely with oxygen, or you could write CO plus DO. It doesn't necessarily matter. Okay? But that is a delta H combustion. Let's call that number 1. Delta H combustion number 2. And this is our delta H of reaction. And if you follow Hess's law, do the cycle, our enthalpy change of reaction, so we go this way, we're going with the arrow for this one, and then we go against the arrow for this one. Okay, so what do we do when we go against the arrow? Subtract it, you change the sign. Okay, so that would be delta H1, or delta H combustion 1, minus delta H combustion 2. Yeah? And it all looks very straightforward. I know it looks a little bit mathematical, but it seems reasonable. I think one of the biggest parts where people fall down is this part here, the delta H reaction. Because that may well be an enthalpy change of formation up here. Okay? And then suddenly people go, oh, it's an enthalpy change of formation. The arrows have got to go upwards. Yeah? And then they end up doing the question wrong. Okay? So you need to look at whatever the data is that you're given, usually in a table. If it's combustions, then the arrows go down. Okay? So, just a little note. That delta H reaction could be an enthalpy of formation. Yeah? I'm sure Mr. Collins talked about that anyway. Yeah? And I'm just completely repeating all the stuff that he said in the past. I think this is about the only topic where our sort of things cross over, by the way. Where you do one thing with him one year and then one thing with me the next year. Yeah? Like I always do the organic. I get the joy of doing organic chemistry with you.
So there is further organic in year 13, right?
Oh yeah, there's some organic. Is there ever? You're going to love it when we get there, but we won't get there until like October, November, something like that, okay? Take a little while. So just take this top part off so that I can add on what happens if we've got enthalpies of formation. So, I'll take a general case again though. So we've got A plus B. We've got our enthalpy change of reaction. Okay, what did we say about the arrows for enthalpy of formation? They go up. Exactly, they go up. Okay, there they are. So, let's call them down here. They're basically the elements that make up A and B. Yeah, they're always going to be the elements on the bottom for your enthalpies of formation. So this would be delta H formation 1, delta H formation 2. If we use that Hess cycle idea, I'm going to do it logically, or at least logically to me. Okay, the enthalpy change reaction, now I go against this arrow for the alternate routes. So what does that make this?
Negative.
Negative. So I'll do that negative straight away. So it's minus delta HF1. I'm going with the arrow there, so I can just add that. Plus delta HF2. Okay? And again, there's that possibility of confusion. Yes, sorry, Nick.
Only do it for A and B, not for C and D.
Well, the elements that make up A and B should be exactly the same as the elements that make up C and D. Yeah? I just didn't really want to confuse everyone by putting A, B, and then C and D as well. Okay? So yeah, again, that element of confusion that can creep in is it's completely possible that this could be an enthalpy change of combustion that you're working out. Okay? But you're using the formations to work out an enthalpy change of combustion up here. Yeah? So it doesn't really matter what this delta H reaction is. It can be any reaction, any time. But it's the data that you're given that's going to govern which way the arrows go. Yeah? So I'll put my note in. Again, it's going to be exactly the same. So, little note is that delta H reaction could be an enthalpy of combustion. Yeah? Now, I've talked a lot. I've tried to ask you a few questions. Does anyone actually want to ask any questions at this point? Is anyone even slightly confuzzled? Ahmed.
So you know how you said that we have to use the data that is provided to
Yeah.
us? So if that was minus, would we say that's combustion? Like, how do we,
Well, you would be, I see what you're trying to say, yeah. So, in a question, it might actually even say, well, work out the enthalpy of combustion for one particular chemical, okay? And it gives you a whole load of enthalpy changes of formation. It may well give you an enthalpy change of formation for water and for carbon dioxide, yeah? And then you would have to build up the Hess cycle yourself, okay? Does that help a little?
Yeah.
Yeah? So I guess the major point I'm trying to get to is that you've got to read and unpack the question properly, okay? Now, pause that for 2 seconds. New definitions. So yeah, some new definitions for our further energetics. Hopefully remember from year 12, we looked at bond energy, okay, or bond enthalpy. And there's my kind of vague definition of it there. So it's the enthalpy change when 1 mole of covalent bonds is broken or formed. Okay, but there is also an equivalent, and it's really useful for ionic compounds, okay, which you've not heard of at all yet. It's called the lattice energy. Okay, and this is going to lead us over the next lesson or two to build up basically like a really big extended version of a Hess cycle that we call a Born-Haber cycle. Okay? Born-Haber. Two separate words. Okay? Named after some chemists, I'm sure. Well, Haber, we know the Haber process. Pretty sure it's named after him. Not too many Habers in chemistry. So, the lattice energy, here's the definition of it. Okay? It is... So it's the enthalpy change when 1 mole of an ionic compound is formed from its ions and it's formed from its ions. The ions are in the gaseous state, okay, not dissolved or anything, or liquid, but they are in the gaseous state. So, for example, someone give me a nice simple ionic compound that we could form. NaCl. Okay, good. So, if we were thinking what the lattice energy would be for NaCl, we would need to take Na plus gaseous plus Cl minus gaseous and form NaCl solid, okay, and that enthalpy change for that reaction would be the lattice energy, okay, or the lattice enthalpy, whatever you want to call it. Yes?
So you can't have a cycle.
You can have a Hesss cycle, but what we will do is we were going to build up something that's actually much bigger than your normal Hesss cycle that we call a Born-Haber cycle. Okay? But the most important thing over the next couple of minutes is to kind of digest that definition, what lattice energy actually is. Okay? Because just like bond energy gives us an idea of the strength of a covalent bond. This gives us an idea of the strength of an ionic bond. Okay, so the more exothermic this is, then the stronger the ionic bond will be. Okay, it's a good point. So this gives an indication of how strong an ionic bond is. And I guess to add to that, what I did just say as well, is that it's always exothermic. So it's always negative, so it's exothermic. Yes?
Why is it the bigger, the more exothermic, the stronger?
So the more energy that's released when a bond is formed, then the stronger that bond is, the more stable that bond is.
But like technically the values, like if the smaller the value, because it's a minus, right?
So the more, that's a really good point actually, Lee. What we want to get away from, particularly when we talk about energy changes, is talking about smaller and bigger. What we really want to talk about is saying is something more exothermic or less exothermic, or more endothermic or less endothermic, yeah? Because if you say bigger and smaller, when you're dealing with both positive and negative numbers, the language gets twisted around very easily,
So
okay?
when you say more exothermic, it's the smaller the number.
So if it's more exothermic, then it's a bigger negative number,
Yeah.
yeah? And that's the way to look at it. Ahmed.
So the charge of sodium, if it was magnesium and take oxygen, would it be a higher because there's more like...
Well, that's something that we're going to actually have a look at, but you're absolutely right. If it's a doubly charged ion, then perhaps that would be a more exothermic lattice energy and therefore a stronger ionic bond. Okay, but we're going to look at the exact reasons and the patterns as we build all of this up. Go on.
If it's more exothermic, it can be more negative.
So if it's more exothermic, then it's more negative. Yeah, exactly. And that's what I mean. We want to get away from talking about bigger and smaller. We want to say more exo, less exo, or more endo, or less endo. Yeah. Otherwise, when you say bigger and smaller, you basically end up losing marks because the examiner has no idea what you're talking about. They can't see from your language what it is that they're talking about. And believe me, even though you don't believe it, I know examiners are looking to be able to award marks, not to take marks away. They want to give you marks. Yeah? Cool. So actually that brings up some really interesting questions already about this. But if we can get that... Are we going somewhere? Yeah. But if we can get that it's just the equivalent measurement, so bond energy for covalent bonds and lattice energy for ionic bonds, then we'll be able to understand this. Okay. There is a whole load more definitions besides. Okay. We're going to look, and I'm not going to put all of them down now, but some of the things you've already heard of. Okay. We're going to need to use ionization energy, which you already know about. So we'll be using first, second ionization energies, possibly even third in some cases. Okay, but the ones you've not heard of that we're going to use, we need to use enthalpy change of atomization, which is basically turning something from whatever its standard state is into gaseous atoms. Yeah? Mm-hmm. And then we're also going to use something that we call electron affinity, which is a new definition as well. Electron affinity is, rather than ionization energy is always removing an electron, electron affinity is adding an electron in to make a negative ion. Okay, so we'll come up with all of those definitions. We'll do that tomorrow, I guess. Okay, we'll do all of those definitions tomorrow and see if we can see a simple Born-Haber cycle tomorrow. Okay, but don't be worried, it's going to be fun. Do like Born-Haber. Thank you, guys.